He leads the team at Google on foam development, and he's also the lead developer of the foam project. Kevin.
Thank you for coming. Okay, so this is going to be something probably a little different than most of you are used to. You probably all know some MVC libraries or UI libraries for JavaScript, but this is something quite a bit different. One thing I should say, that when I came from previous presentations, there were a lot of questions whether this was some kind of hoax or a presentation art or some kind of vision of the future, but it's none of those things. This is a real project, although I take that kind of flattering that people would think so. So it's open source. You can go to foamdev.com, see the source. You can run these slides, run all the demos that you're going to see. Everything that you'll see is open source except for one slide, and everything is a foam program, including the presentation. So this is really a case of the medium being the message. Everything that you see is foam, including this animation. So it's the feature-oriented active modeler, and it's which is called a modeling system. So if you've ever heard of model-driven engineering or model-driven software development, that's what we're talking about. Okay, so the heart of it is a model. So, sorry. A model is basically like a high-level definition or a blueprint or a specification. And so the idea with foam is that you want to create high-level definitions of your software and then let foam fill in the, generate a lot of your app from it. And the things that it's creating are called features. So in the name, it's feature-oriented active modeler. So you create models, and so we have a list of models down the side here. And then as I hover over them, you can see on the right. And so it's sort of like a class where you have all the different properties and methods and other things as well. And then the features are any kind of abstract or any kind of generic feature that we derive from that. So help text, a detail view, a table view, XML support, JSON support. And this column is interesting. So from the same model, not only do we generate JavaScript, we can also generate Java and Swift code as well. So this is really meant to be cross-platform, although this is TorontoJS, not TorontoJava, so we'll stick with JavaScript. And we recently started adding Swift support as well in the UML diagram. So you can see in this grid, I have 22 models going down the side and 10 features going across the top. So that would be 220 components, which would be a lot of effort to write. But in foam, you just write the model, and then you either write or reuse some existing feature, and foam creates all those features for you. Okay, now we're going to go back and give a little bit of a history lesson. So, anyone know what the largest engineering project of the 1960s was? Pardon? It was putting a man on the moon. Was the largest engineering project. But the number 2 was the IBM System 360. So creating an operating system was such a huge effort that competitors for that wanted to create an operating system called Multics, and that had to be a combined effort between AT&T, MIT, and Honeywell, or no, General Electric, sorry. And so what this is, what I'm running here is a simulation. And so these little blue dots represent developers, and they're running around in these little cells writing code, and the code is green. And I've broken this up into the same kind of diagram we saw in the first. So here are all the types of data you would need in an operating system: users, groups, processes, devices, files, and then all the features you need: sorting, search, paging, printing, editing. And so as they implement a particular feature for a particular type of data, the developer is going into that cell and writing the code. Okay? And then we can see the lines of code that they're writing that's growing, and then the utility that they're doing. Okay? And then the efficiency, which is constant. Now in AT&T, in the basement, 2 developers created Unix, and the name was a pun off of Multics. And what they did was they had the same data and the same features, but they made all of those functions reusable. So if you use Unix, you have commands like sort and grep and more or less. And they do that just once. And then you use a pipeline and you compose all those features. And then the individual commands, they're kind of lacking all that functionality. So the Unix philosophy is do one thing and do it well, but really what's the most important part is that you only do it once. So as you can see now, despite being having 50 developers, or 50 times as many developers, Unix has overtaken Multics in utility at this point, because they're basically doing a more efficient algorithm. So, and now all kind of modern operating systems like Linux, Android, Chrome OS, Mac OS are all derived from Unix, and Multics is gone. Another thing they did that was controversial at the time is they wrote Unix in a high-level language, whereas Multics was written in assembler. And then through time, as new hardware came on, they could port that high-level C code to different new platforms. So as new platforms came, they just kept porting it to those new platforms, whereas Multics faded into obscurity with the hardware it was written for. So there's really two lessons from this. One is writing at a higher level so that you can target different platforms, and another is the kind of exponentially better efficiency of only coding features once. Okay, now back to foam. And so really what we're trying to do now is, that was great for the command line, but once we went to GUIs and then once we went to the web, that kind of exponential efficiency didn't carry over. Okay. So foam is holistic, or you might call it full stack. So if you look at a typical application that you might write, we're starting on the left. We have our issue SQL, or it could be whatever type of database you're using. In this one, we have a backend server in Java. We're using protobufs to define our middleware, and then we have a front end in JavaScript, and these are all the components, and then the front end of the front end in HTML, and then CSS. So this is written in 1, 2, 3, 4, 5, 6 different languages. And this is if you're only supporting one front end. If you're going to support iOS or Android native apps as well, then you're going to duplicate everything on the right-hand side. So who's here has heard of the dry principle? Okay, so it means don't repeat yourself. And so the concept is you don't want to be duplicating anything in multiple places in your code for two reasons. One, it's more effort, and then it can cause reliability issues if you update it in one spot and not in another. And I worked on at Nortel once, and we had this sort of architecture, and I was doing the front end of the front end in Java, and the back end was written in C++. So there was me on the front end of the front end, a guy on the back end of the front end, a guy on the front end of the back end, a guy on the back end of the back end, a database guy, and a reporting guy. And it may sound like a contrived example, but it's true. We wanted to switch the last name. There was one guy who had a bigger last name than the database would support, and we had to change this in more than half a dozen places. And then always somebody was on vacation in their part, and we had to duplicate it. So within each language, you may think, I define this as a constant, that the last name is 35 characters, and I'm not repeating that, and I'm nice and dry, but that's only in my part of the system. Across all the languages in the system, I'm not dry, right? And so if you think about it, the fact that the person's last name is 35 characters should be in one canonical place. Even the fact that they have a last name should only be in one spot. And so whatever language I write that in, then that doesn't help me with the other languages. So I need something above all the languages that I'm targeting. And so we get asked a lot, like, how do you compete, or how do you compare with Polymer or Angular, which are other Google frameworks? But that's over on the right. That's the Vue library. The Google product that we are really most similar to is something called protobuf. So here we create a model definition in protobuf, and then it generates the stub and skeleton code to marshal that across the network. But this is, so it generates these two for you. But what we do in foam is we get rid of that, which is also a model, and replace it with a foam model, which has a lot more information. And then that lets us generate the system all the way out to both ends. So we can generate the database for you and the client. And then it's just up to you to insert any business logic or custom views or custom styling. But right off the bat, from a model, we should give you a working system. Or systems. So you can see here, also we do search and client-side data storage if you need it. And as you add more platforms, like we also support Android, and we recently started, as in yesterday, on Swift, we handle that as well. Okay. So models are probably, you're probably already using models and you're not aware of it. Classes in object-oriented languages come from models. The classical inheritance comes from a language called Simulus 67, which was from 1967, which was for modeling simulations. And the type of prototype inheritance that JavaScript has comes from frame-based knowledge representation systems, which were ways to model knowledge in the 80s. So they both derive from that, but they're kind of historic modeling systems. And so what we want to do is take a modern modeling system and use that as the basis for programming, which works great in JavaScript because you're missing a lot of the things that you would normally get in a lot of other programming languages. So here's like a little Pong game, and if we have time at the end, I'll go through the code. And it reads really nicely. So you can see, here's the code. We've got package, so we have packages, then you list your requirements. We have, you can say what model you extend. You have this.super. We had traits for multiple inheritance, constants, properties, which are like high-level instance variables, methods, listeners, actions, inline templates, property change events. Also, we have reflection and type checking. And we don't do this through a transpiler. We just do this by compiling the model on the client. So if you want to use a transpiler like CoffeeScript or an ECMAScript 6 transpiler, because we don't do that, you're still free to do it. We also, here we have a little Minesweeper game. Oh, I died right off the bat. Okay, didn't get really lucky. But we have basically 3 classes or models in this game, a game, a board, and then cells. And we provide dependency injection or dependency management or inversion of control. So in the board, we say that we export it as board. And then in the cells, we import board, and then they have access to that. So you're not like going around and fishing for other objects in the system. Every model declares its imports and exports, and then you pick them up through the dependency. Or you can provide them if you're mocking for testing just in the constructor. So foam objects are very self-centered. Everything is like on this. So it's this.board or this.whatever. So as far as you know, you're the only object in the system, really. Okay. So model types. We model entities, which are like classes, which we just saw. But we model other things as well, animations, database queries, and that way we can connect to different databases and the queries will still work. Parsers, interactive documents, which we call flow documents. And this presentation is itself a flow document. And we have something called the Chrome App Builder. If you're doing kiosk or digital signage apps, Chrome OS is good for that. We have an app that you can use. It's in the Chrome Web Store, and it helps you model and those type of apps, and then it'll build them for you. And that has over 20,000 users. And so what we're really trying to do with Foam is kind of extend the reach. On the one end, we're trying to lower the barrier so that people who are maybe not even programmers, so the people who use the Chrome App Builder, they just fill in a form and it makes the app for them. And then on the other hand, we're trying to kind of extend the reach of more experienced developers. Okay, so I said we model animations, and here's one of the Foam architecture. So on top of JavaScript, we have a rich event system, reactivity, then animation, model view controller, metaprogramming, and then a modeling environment. But we can use it also to generate Java, Dart, C++, or whatever. And this is the developer, back from the earlier slide. And one thing with kind of high-level frameworks is they're very good at what they let you do, but sometimes if it's not something that they enable, you can't do it. But Foam, we're very careful that if there's something that we don't enable, then at least we don't make it any harder. And so you're free to go down at every level. So if you go to to2mvc.com, how many people are familiar with that? You can find the Foam entry there, and it looks exactly like all the rest, but it's quite short. Something's wrong with my slides. Oh. Okay. You can have a look at the source. Okay. So, although we have mentioned we have an MVC framework, we have a lot of support on the back end on the database. So that's what we call we have a generic interface for that called a data access object, which is how we store data, irregardless of what's the database, whether it's IndexedDB, MongoDB, some Java server. We have all these different implementations, but they all implement the same interface. And then our client code just uses the DAO, and we can move between databases or add caching or offline, and none of the code changes. So just the kind of standard methods you would expect: put, remove, find, select, listen, pipe, where, limit, skip, order by. And so on the right, we can see an example. I have the DAO. We can say skip 200, limit to 50, order by emails timestamp, where the emails to me from my mom, timestamp since start of the year, and then group by subject and count. And so even this even works on arrays. So if you go to a relational database, it supports all those features, so that's not a big deal. But if you go to just an array, we make up the difference. Okay. And so here's different kinds of DAOs that you could say. We can go to local storage or IndexedDB on the client side. IndexedDB is quite slow, so we can add caching to that. We can go to a simple array, Chrome storage, sync storage. We can go across the network to a server. And also we can add a lot of called decorators. So the underlying DAO might not support logging or timing or validation or data migration. And we have like Legos that you can just insert before that, and they will add that functionality for you. And our caching layer is very smart and can speed up. This is a benchmark done by another team. We're comparing the DAO versus IndexedDB versus WebSQL, and it's on average 100 times faster. So here's an example. So this is an Olympic medal database, which has 29,000 records. And you can see I can sort, they're all here. I can just scroll all the way. But I'm not going to do that. When I pick, say, the from year, I don't think you can see that. It's fast enough that it can go and do the count on every year. So before I pick any year, it tells me how many I'm going to get. And then it selects filters it out. And then the cities, it knows how many, all the disciplines. So this is what we call reciprocal search. So every time I do a search, you can see the results are instant, but then I can do every possible next search, and I've filtered all the other axes and have all the counts for those as well. And you can see the gold, silver, bronze, and I don't even have to click. It's fast enough that just as I hover over those entries, I update the table. And you can see as I hover over the color, the gender column counts update as well. So when you can do things like 100 times faster, if you do it 10% faster or 100% faster, that's nice. But when you can do something 100 times faster, then you can kind of fundamentally do completely different things. Even here, we could do search, and I could say, so search for columns we don't have, we can find all the Kevins, And that's right away. So you have the full search that you have from normally like a Google search from the server, but this works even when you're offline. And I've got and, or, not. I've got the full Google query language. And this app is only 236 lines of code. And I can also pick my columns. And so it's quite small. But what we can do also is I can run this Node.js Olympic server. And now I'm going to serve that DAO over the network. Then I have another, not that one. So this one here. Nope. Okay, so this is a client version. And on this one, all the data, it's doing, so you can see it's a bit slower because all the data is coming across the network, but it's still very fast. And so the interesting thing is, I completely changed the code from going to IndexedDB to go to the network, and I only changed one line of code on the client. I said instead of having an IndexedDB, a cached IndexedDB DAO, I want a network DAO, and everything else stays the same. And I get the servers basically for free. Okay. Okay. So that's shows the. I lost my presentation. Okay. And idea, if you wanted to switch that to a Java server, then again, we can do that for you. Okay. So one thing on the, we also have a view library, that's the DAO part, but also for views, what we wanted in our modeler, some models are text-based, but some are graphical, or at least have a graphical component. So in our view library, we wanted to have the ability to support graphics. And we didn't want to have a different library and a different way to do everything when we're doing graphics, and another way when we're doing regular DOM HTML. So our view model unifies canvas views and DOM views. So you program them exactly the same. So we have data binding here. I've got this value here, and I can increment it or decrement it. And then I have a graphic view. But when I give you that view, you can't tell the difference. I give you a view, and you can use it, and you bind data to it. You can do event handling, you do configuration, composition, reaction, animation. Everything is exactly the same. Whether that's Canvas, WebGL, DOM, or a combination, you don't know. It's the same programming model everywhere. Event handling, so this is a Canvas button to give, okay. Configuration. So I have a circle, and then I can see the properties for it. Okay. Pink. Then I can configure it like normal. Composition with DOM, you can add elements to other elements and compose them, but you don't really have that in Canvas. But here I would take a circle, take two circles, compose those into an eye, compose two eye into eyes, and then compose that into this little dragon creature. Then reaction, which is something you don't actually have normally in DOM. I can make things react to other objects in their environment. So he's following my mouse around. We can get animation. Now you have CSS animation, but that doesn't help you for Canvas. And now I can do that the same way, whether it's Canvas or DOM. And then I have interpolation, so even if I want to animate something, I can say how I want to get there. So they all start in the same spot and end in the same spot, but they take a different path. You can define any function, and it'll interpolate it between there. And I can animate anything, DOM, Canvas. I could animate somebody's salary, and it would change over time. It doesn't matter. It's completely standardized. So here's, if you go into Chrome, you have the task manager. Here's a prototype of a kind of new and improved one. And this is like, it's common that you would want to mix DOM and graphics. And so you can do that easily. Oh, actually, and seamlessly, you can have both types running in the same app, and it doesn't matter to you how they're implemented. And you have the same search here. So if I just wanted to see, processes using more than 500 meg or more than 50% CPU, that works. Okay. So we had that thing before, reactive programming. Set the mic down for this. So here I have a mouse and I have a clock. And I've said that I want the clock's X and Y to be the mouse's X and Y. And then it just happens. It's like a spreadsheet. I don't need to have listeners and callbacks. I can just declare that I want that to be a permanent relationship, and then it will react. So when I talk about reactive programming, that's basically just like spreadsheets broken out of the spreadsheet. So as I move that around, it takes care of it for me. But we can do something a little bit more. Okay. My run button is missing. There we go. So I say clock 2 is clock 1's X plus 200 and clock 1's Y plus 200. And now I'm conform a chain. So clock 1 goes off the mouse and clock 2 goes off of clock 1, which itself goes off of the mouse. So you can create these whole graphs of dependencies, and there's no listeners, there's no duplicate events, there's no any of those kind of errors. I can even do, but wait, there's more. Get rid of that. Now this one is a little bit more complex. It's the same idea, but I've modeled time. So in here I've say timer.time, but otherwise it's the same. And now when I run this, because it's a function of time, this gives me animation. So we didn't really make an animation system, we just made this reactive programming system. But there's nothing special about time, except it's kind of changing, and then you get animation for free. So that animation that you saw before, that's just all done this way. And this is very simple, but you can do quite complex things. So really the whole thing is like I said, it's like a spreadsheet, but I have graphics and I have other type of objects, and I can break it out of the grid confines. So here, this animation, I've got a bunch of planets orbiting the sun and moons orbiting planets. These eyes are watching Mars. This graph is graphing the position of one of the planets. We've got a clock. And so that's all going, and this is all by these kind of reactive declarations. And so it's much easier to program because you don't have all this listeners and callbacks and stuff. But here you can actually see the time. This is the time model, and it's changing. I can stop it, I can step it, I can start it. And so it's just a regular object that I've modeled. And this is a time wheel, and it's reacting to time, but it's not a function of time, it's actually a relation. So it's not a slave, it's a peer. So if I grab it, now I can control time. And now I can kind of spin time like a disc jockey, right? So you could make a game where you program something, you blow up and you can stop, go back, continue from there. So it's kind of neat. We can do lots of cool stuff here, and the coding is much simpler than it would be otherwise. Okay. No, we can put in any formula there, but if those formulas happen to be laws of physics, then we get a physics engine without actually having to have written one. So here we've got gravity and friction. I just put negative gravity on these bubbles, which makes them buoyant, and the other ones are falling down, and I added some friction so that the viscosity of a fluid, and that gives me this. But it's the same reactive programming as before. Then I can do collisions. I can do springs, collisions and springs, balloons. I'm not really sure what this one shows, but it's fun. So just from this one, reactive coding thing, it's a simple thing built right into the, I would say, language. Often we refer to foam as a language, although it's not. It's entirely JavaScript, but it really has the feeling of being a different language. Okay, so one thing I didn't mention before was our models are modeled, which kind of gives us some interesting bootstrap issues, but it makes foam very small, because we say if you model something, we can generate all these features for you. Well, then if we follow that advice ourselves and we model our model, then we get all those features for free. So if we want to take a model and store them in a database, or get a detailed view, or do any kind of other things, we get that for free, which makes foam very small and compact. So, but since foam's models are data, here's the code, the methods for this dragon. So if I want to go chop off his tail, okay, and create kind of a bat, I can do that. Now I can go up to the feather. Let's rotate a little more. So you see, I get the error message right on the keystroke. I'm rotating a little bit more. It's a bit big. Let's try that. Now that's a little fast. So let's go up. We have our timer. We have a time warp. We can slow that down. Okay. And so we can do this sort of thing. And if you couldn't kind of explore, with the code, it would be very difficult to find out that you would get this sort of effect with the traditional, compile run loop. And then we can grab it. Okay. So again, this is just, we got live coding, and just like animation and physics, we got it for free because everything is uniform, and we're just reacting to the code that implements the functionality. So there you go. That's pretty nifty. Okay, so in the MVC, we covered DAOs, which are the model, our views, where we combine both graphics and DOM. But one thing that's usually missing is controllers. And this is where kind of Foam really stands out, in that we have reusable controllers. If you consider Outlook, the email client, and iTunes, the MP3 player, those are almost exactly the same application. They've got the same categories on the left, some search, a table view, and then when you pick one, you get a detail view. Except for one has emails that you can send and reply to, and the other has MP3s that you can play. Those are almost the exact same app. And in Foam, they would be. So on the left, we have, this is a code site issue tracker, and on the right, this is a Gmail client. So these run, if you click on these in the demo, you can actually run these. And they're both about 1,000 lines of code, which is at least, much more than 10 times smaller than the next smallest Gmail client. And those two apps share 98% of the same code because it's reusable, and we just put in a different model and we get that app for free. So a lot of things, you would create the model and you'd create a custom view for the citation and then customize the detail view and any kind of other custom actions or business logic, and you're done. And now if I wanted to add into my email client, say when I get an email to bug, actually have the bug tracker GUI embedded right in my email client, or maybe I wanted to also add RSS reader or groups or some other features to my email client, my client size is not going to grow by 100, 200, 300%. It's going to grow by 2, 4, 6% because all the controller and the framework are there already. And just about that, Foam is 60K for Hello World. And then after that, it depends how many models you have and extra features you bring in, but it grows very slowly. So the biggest app we have, or one of the biggest apps we have, is only 110K with about 20 screens and internationalized and images. So they tend to be very small. Okay. So Brendan Eich, the inventor of JavaScript, said that he considers JavaScript to be a dialect of Lisp. And Lisp is a programming language that's famous for metaprogramming. And the reason it's good at that is because it's a language for list processing, but the Lisp code itself is lists. So it's very good at processing lists. Its own code are lists, therefore it's good at processing code. Well, we're actually kind of treating Foam the same way. So Foam is a framework for dealing with models, but Foam is itself modeled. So this makes metaprogramming very easy. And normally when I say metaprogramming, people's eyes kind of glaze over. But all that means basically is toolability. Any program which is either reading code or writing code, that's some kind of basically metaprogrammer. So that includes API browsers, code generators, type checking, linting, refactoring tools, templates, syntax highlighting, beautifiers, minifiers, code coverage, unit tests, editing, and code visualization. So normally this sort of language level metaprogramming and tooling, that's like a different kind of programmer than, say, somebody who does some kind of e-commerce site. But in foam, it's the exact same because the foam models are modeled, they're stored in a DAO, and you can look at them with your regular views. So the same code, same type of programming, and the same APIs, you can connect to your DAO of models and do a query and produce, say, for example, a UML diagram. And I just went through the API docs, and I grabbed one that looked cool. And I didn't even realize till someone else on my team pointed out that this is the model doc diagram. This is the model of itself. So normally you have something where you would generate like a Java doc or type system, and you would run that statically against all your code, and it would analyze it and generate a bunch of HTML. Well, this is just like a normal foam program. We connect to the DAO, we do a query, we find all its properties and methods, and then we generate the form. And then we generate the UML diagram. So there's nothing different about this type of programming. And if I wanted to take all the code that, extended one model and change it to extend another one, like a typical refactoring, I could just go to the DAO and do a query and say, update everyone who extends this, and make them extend that. Okay, we have this little tutorial app. You can do search, and we have that, and we have an extended to do MVC tutorial. So if you I think we might do a tutorial here at the Hacker Night coming up. But if you're on your own time, you want to go through and learn how to do some foam programming, that's a good place to start. So on Chrome OS, there's a system calculator, and it's written in foam. So this is deployed, this is standard, it has millions of users. It's internationalized, has accessibility, and you can get all these functions. So it's similar to the one on Android. Although the code is 6 times shorter than the Android version, despite having 2 extra panels of functions. And now this is what it looks like normally. So we model the calculator, and we just want to bring up a detail view, and that's it. And so this is actually a working calculator. You can see all the buttons, and I can try them all out. And it has history. Now it looks terrible, but you got it for free. But the only difference between this and the previous one is we threw in a template, we moved the fields around, and we did some CSS. So believe it or not, this and the other calculator are the exact same. And so all the two-way data binding and hooking up the actions and everything that's done for you, then you just have to rearrange the position. And these, to get this effect, these are canvas buttons. We have another simpler version with DOM buttons, but the code doesn't change. Okay, so I'm just going to explain this graph. So if you look, this is similar to the Unix simulator we saw at the beginning, but this is a Google simulator. It also started with 2 developers, Larry and Sergey, and they only had one model, web pages, and one feature, which was search. But then over time, they've added more types of data and more features, and then they've added more platforms. So this is exactly the Unix model. And so what Google is essentially doing is trying to make an operating system for the world's information. And their motto is to make the world's information universally accessible and useful. And if they're trying to do that by filling in each of these cells individually, that's a very inefficient way. And if we can get them to move to the perimeter, follow the Unix and foam model, then that's exponentially more efficient. Okay. So foam is model-oriented. Models are themselves modeled. This gives you many language-like features, better toolability, and cross-language dryness. It's feature-oriented, and the features are any kind of these reusable features that once you write it once, you get that feature for every model. And we have about 50 of those now. We have reactive MVC. From the reactiveness, we get observerless coding, animation, physics, and live coding, almost for free. We have models, we have DAOs, which is our generic technology-independent database API, We have views, and they're also technology independent, so it doesn't matter if that's a WebGL, a Canvas, or a DOM, it's transparent to you, the programmer. We have very good support for mobile, and the small size helps out there. We have reusable controllers, we're cross-platform and cross-tier, and basically we're creating an operating system for information. Or to summarize, the summary of the summary, efficiency is really Foam's value proposition. So we're talking about application performance and developer efficiency, or as we like to say, fast apps fast. And I can show you that. And I can run all 25 programs that we had at once. And so right now I have 50,000 objects, 20,000 data bindings, one and two way, and some of them quite complex. We can see the changes to the dragon we made are still there. The graphics is still going smoothly. And this is all just in one web page. So that's it. If you have any questions.
Awesome. Thanks so much, Kevin. I actually have a question for you, too. How did you do that? How did you manage to blow every single person's mind in this audience room right here? That was incredible. Thank you so much.